I don't want to get but I can never get a hat trick. From what? I've never gotten a hat trick ever.
Not even against West?
No. The most I've gotten in a game is 2.
Yeah, that's right.
I only 2. I can get 3 though. It is. It's still
I got 2 black games. I got 3. Out of the goal, then we can win again. I can have a light
I'll see.
I think it's fun.
You 3, 4, 6, 7, 8, 15, 16, 17 school function.
I have some it was like hot at the start.
We're 18. We have a supervised adult with us. Sophia's 18, so we have a supervised adult with us.
A supervised adult?
Yes. An adult who you keep an eye on.
Yeah, Sophia's
Supervising adult.
an adult that supervises us.
She's not.
No, we're gonna be supervising her at most. But she's 18, so I'm pretty sure she is.
I didn't wake up yesterday.
I thought she was.
And that's it. I was on TV.
All right,
Yeah, I didn't move.
That's the worst.
KP,
What?
name me an element name me an ion, which means you have to give it a charge, that is isoelectric to neon, argon, or krypton. Go.
Oxygen plus 2.
Which one is it isoelectric to?
Neon.
Oxygen plus 2, isoelectric to neon. Sophia.
Why is it plus 2?
Oh, I'm sorry. It's not plus 2. Sorry, my bad. What is it?
Oh, minus 2.
Minus 2. Thank you. Sorry. Good catch. Yours.
Oh, me?
Yeah.
Fluorine -1 to neon.
Good. Olivia.
Nitrogen -3 to neon.
Good. Leaf.
Chlorine -1 to argon.
Chlorine -1 to argon. Good. Alexis. Wow, it's a shock. I'm working my way around the room, and everybody in your area just got cold, and you're like,
Sulfur.
me.
Okay, let me talk. Sulfur -2 to argon.
Sulfur -2 to argon. Good. You're Itzy.
Phosphorus -3 to argon.
Phosphorus -3 to argon. Good. Angel. I know you weren't here yesterday, right? But listen, because I have great confidence that she can figure this out very quickly, unlike you. Fluorine -1, isoelectric to neon. Oxygen -2, isoelectric to neon. Nitrogen -3, isoelectric to neon. Chlorine -1, isoelectric to argon. Sulfur -2, isoelectric to argon. Phosphorus -3, isoelectric to argon. Give me another example. Doesn't have to be to neon or argon. You know what? I'll open it up to any noble gas you want. Okay, what would it be? Its charge.
-1.
And what would it look just like? What is it? What noble gas is it isoelectric to?
To argon.
No. Chlorine was to argon.
Oh, so
Fluorine was to neon. Bromine. Very good. See, KP, have a little faith.
I never said I didn't have it.
Good, then tell me what it means to be isoelectric.
To look like it.
In what way?
Electrons.
In its electron configuration, it means it would have the same configuration as that noble gas. Yes, which one of mine do you want? Okay, I'm sending them over.
him. Me.
Ask them if they want me.
Tell them to take
Tell them to take me. Pick me.
Make sure you're giving them the right one then. Because there should be ones for these.
You're talking to the wrong person, because who's the one person in our department who doesn't have to do this?
This is pretty interesting.
So you may have to ask Emily, but I'm pretty sure you're probably looking at the wrong list, giving them the wrong number. You got to find your class from this try. They should be labeled because Amanda had gone through and done that for us. So, okay. Sorry, not a problem. But they don't want you. But I do. Go ahead.
Wait, who's Amanda?
Silicone. Argon.
Silicon what?
-4.
-4. Isoelectric to argon. Good.
Wait, what about magnesium? Would that be isoelectric to argon too?
Nope.
Would be neon, right?
And magnesium would be a what?
2. A positive 2.
And it would be isoelectric to what?
To neon.
Good. Okay, don't steal them all. Ifra.
Amanda.
2. Okay, I'll let that one go. That would be a major exception, but I will let that go because your thinking is absolutely correct in that. Mitzi. Is not one of them. Where is up here? Tell me. No, already done. Everybody apparently likes negative ions. Nobody likes positive ones.
Magnesium, positive 2.
That's the one Cynthia just said.
I'm here.
What?
I didn't hear.
What?
I was listening.
What?
You're not funny.
But she keeps leading right into it. So go ahead. Come on. Give me an answer. Give me an answer.
Just very relaxed.
I know. Lizette should be worried because she's next.
Sodium,
Okay.
positive 1.
Yeah. Very good. Sodium positive 1 to neon. Magnesium positive 2 to neon. Go for it, Lizette. This is the easiest thing you're going to get this unit.
No.
Is this on the
love
test?
it, though.
Yeah.
Is on the quiz?
I haven't written the quiz yet, so I don't know.
When's the quiz?
Wait, there's
I haven't written the quiz yet, so I don't know.
Oh my god, can we do it next week?
Maybe.
Let's do it next week, Monday.
I thought it was this Friday. I was
So you want it on Tuesday?
Yeah.
Lizette, today.
Quiz. Okay.
I just had everyone in the room hate me for like
You did. It was kind of impressive. They turned on you so fast.
Yes, I was like chilling.
It wasn't like that.
Well, if the test next week Monday, then we have to be here. I can't believe it.
I need to play the Jeopardy theme music because they're going at it back there talking about this. Lizette! Come on! Two. That's it. Point it out for her. Very good. Helium. Good. Farhan.
These gonna be all the elements that are on
What? Okay, 1, bromine, -1 is not to argon, and 2, we've already done bromine, -1 to krypton. What? Which one? 76. You're going to do that one? Don't do that one. We don't even know what kind of ion it would be. Why are you going back to argon? Because you like argon that much? Chlorine was to argon, sulfur was to argon, bromine was to krypton, fluorine was to neon, oxygen was to neon. What's iodine to? Okay, then say Xe at least. I can go with that. Xenon. Good, Rose.
CS plus 1,
Yep.
2, X, E.
To xenon. Good, Aiden. Potassium what though? Good. To argon. Good, Ava. Come on, we just did 18 of them. What?
Barium to xenon.
Barium to xenon.
Yeah.
Barium to xenon. Barium what? Because it's got to be an ion.
+1.
So barium is now a +1 ion.
+2.
Barium is now a +2 ion.
Yeah.
Okay. Okay. But again, see, if we were listening at things, you got time to do your notes. Do them in a minute. Okay. Olivia. Rubidium +1 to krypton. Good. Jennifer. Calcium +2 to argon. Good questions, ladies and gentlemen. Isoelectric means to have the same electron configuration. Any element that becomes an ion is always isoelectric to a what, Alexis?
Noble gas.
Right, because noble gases are what, Cynthia? Noble gases are what, Sophia? Stable. Atoms are trying to become stable when they become ions, so they are going to have the same electron configuration as something that is already stable. Okay, here's the bonus question, ladies and gentlemen. What would hydrogen be isoelectric to?
If you take one away, then it's 0.
You're right, but what could you do with hydrogen?
You could add. So it's be helium.
Okay, remember, technically hydrogen is a what?
It
A
could
non-metal, which means it should gain 1 electron, and then it would be isoelectric to helium. Good, 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 good. Questions? Wonderful, wonderful, wonderful. I think we left off talking about somebody who's not very exciting yesterday. I believe we were on Niles Bohr. We were on Thomson? We didn't get to Rutherford even?
Oh, no, you did.
No, we did.
We were talking about Rutherford because I showed you the periodic table from when Mr. Arts was a student here. Okay? The one from 1930. Okay. So Bohr, ladies and gentlemen, proposed a quantized electron, meaning electron has a certain amount of energy. Meaning that if an electron will move from one energy level to another, it will take a certain amount of energy to get it to go to a higher energy level. But when it goes back down, guess what it does with that energy? No. Gets rid of it. In what form? No. Energy in the form of atoms? Come on. No, not heat. Light. This is the idea behind fireworks, ladies and gentlemen. This is why different elements produce different colors of fireworks, because when the electrons move from a higher energy level back down to a lower one, that is a certain wavelength of light, which is related to energy and frequency, like we talked about at the start of this unit with EMR, which then produces a certain color of light that we see in fireworks. By the way, Bohr said that the electrons were not orbiting around the nucleus like planets around the sun. He said that the electrons were in energy levels, ladies and gentlemen.
How does he figure that out? We can't see them.
You're right, we can't. But by knowing how they would jump from one to another and then come back down and release different wavelengths of light, he was able to figure out how much energy there was. Which is why the next guy was so very important, because the next guy is someone we've already talked about, Planck. What did he do? You have him on your yellow sheet. You already have an answer for him. He was the one who gave us the constant that relates energy and frequency. Okay? He is the one who also gave us quantum mechanics, ladies and gentlemen. You could say thank him for those 4 quantum numbers that we just went through, ladies and gentlemen. Planck gave us those. He created quantum numbers. Questions, ladies and gentlemen? And yes, he did give us the constant between energy and frequency for light. Okay? Between energy and frequency for light. Questions? Can I move on? No one said no. Next is Moseley, ladies and gentlemen. Guess what Moseley actually did, ladies and gentlemen?
Found protons.
He found the proton. By the way, this is about 1930, 1940, somewhere in there. So 100 and some years ago. Okay? Not even. Moseley found the proton, ladies and gentlemen. Okay? He's helped rearrange our periodic table so that it's set up by atomic number. It still is Mendeleev's periodic table, but now we have another thing that we can add to it, atomic number, ladies and gentlemen. Okay? Questions? Heisenberg. Heisenberg gave us something, ladies and gentlemen, called the uncertainty principle. He gave us what is called the uncertainty principle. And basically what the uncertainty principle says is that you can either predict the speed of an electron or you can predict its location, but you cannot predict both at the same time. You can't do both. You can do one or the other. You can tell how fast the electron is moving or you can tell the area where it is moving, but you cannot mathematically calculate both at the same time. That is what is called the uncertainty principle. Anyone need more time? Wonderful. Last slide, ladies and gentlemen. Pauli. Pauli gave us the exclusion principle, ladies and gentlemen. He gave us the exclusion principle, which says that no two electrons can have the exact same set of 4 quantum numbers. No two electrons in an atom can have the exact same 4 quantum numbers. That is why the magnetic spin is either plus 1/2 or minus 1/2, up or down, left or right. I don't care how you want to describe it. But that is the reason you can only fit 2 electrons into each orientation of a suborbital. Because otherwise, if you put 3 in there, the quantum numbers would repeat. And you cannot do that. The exclusion principle says each electron around the nucleus of an atom has to have a unique set of 4 quantum numbers. Questions? Wonderful. Avogadro, we've already talked about. Avogadro gave us the mole concept. Formula mass of everything is related to carbon on the periodic table. Do you really think they actually went out and counted up all of the carbon atoms in the universe and divided it by the number of carbon atoms to get the average atomic mass? Heck no. But relatively speaking, everything on the periodic table is related to the mass of carbon. In other words, hydrogen is about 1/12 the mass of carbon. Helium is about 1/3 the mass of carbon, and so on and so forth, ladies and gentlemen. Everything relates to carbon. Newton, ladies and gentlemen, gave us the figs. Fig Newton. No, Isaac Newton said white light was made up of the colors of the rainbow. White light is actually Roy G. Biv, ladies and gentlemen. Red, orange, yellow, green, blue, indigo, violet. Did I say violet or violet? Okay, thank you. I thought I was getting violent with you. All right. Questions on the scientists? No, I will not. But the notes are online and the videos are online and you can check them out anytime you want. Questions?
Van der Waals not a scientist.
Nope. Type of force.
Van der
He
Waals,
may
yeah.
be a scientist, but he didn't work with the atomic theory. He worked with the forces that hold atoms together. Okay. Okay. All righty. So, the element named after the scientist who gave us the law of octaves is the lightest element of all on the periodic table. Newland? Okay, good. Now what's hot?
What was the other part of it?
The lightest element of all.
Hydrogen.
Hydrogen. Very good. By the way, This is why I was amazed in the first trimester when someone got a 2. To me, that is a slam dunk, no-brainer question. You should know where the lightest element on the periodic table is, and yet someone got it wrong. Okay? Or they didn't know who the scientist was who gave us the law of octaves. That could be a possibility too. So, questions? No? Wonderful. Good. Let's talk about periodic table trends. Okay? Now, this, ladies and gentlemen, is where you're going to want to pull out those periodic tables that I gave you that have the periodic table this way and that have the periodic table this way and this way. Now, by the way, again, I don't think you should have to, but I would maybe take this periodic table, and in that spot for hydrogen, I would maybe put lightest element of all. Lightest element of all. So if we're going to do that, ladies and gentlemen, we should probably go in the lower right-hand corner and write what? Heaviest element of all. By the way, ladies and gentlemen, as long as we're putting things on there, let's do this as well, ladies and gentlemen. No, it doesn't. I do that so that you have plenty of room to write what you want. Okay? Ooh, we're going to get to that today, yes.
Wait, are you going to have us write on both sides? Or the...
You can write on both sides. You could write on all 4 edges if you want, Cynthia. Go for it.
No, but for the final, are we turning these in?
No, why the heck would you turn that in? That's your notes. From the 7th period, the 3rd element, all the way to the end, those are all man-made elements, ladies and gentlemen.
So you're gonna say like it's a man-made element.
So this man-made element is named after the person who gave us triads. And it is the one that would be a -2 ion.
Oxygen.
Really? Oxygen is now at that bottom part of the periodic table?
Oh.
It would be Dobereiner. He's the one who gave us the triads. It would be this spot right here, ladies and gentlemen, the -2 group down at the bottom.
Oh, where LV is.
Correct. Okay. Questions?
Even though it's like underneath the staircase.
What?
Even though it's underneath the staircase, it would still be a negative.
Yes. It's in that's the group that it would be in. Okay? Because we didn't describe that as a +5 or a +6. So it's a -2 group. These elements here, ladies and gentlemen, these 4 differ by 11 in atomic number. Even though they are right next to each other, they differ by 11 in atomic number, ladies and gentlemen. So what we are talking about is calcium to gallium. Even though they are right next to each other on this periodic table, they differ. Ooh, yes. They differ in atomic number by 11. Strontium to indium differ in atomic number by 11. Questions?
Does that say in atomic number?
Differ by 11 in atomic number. These differ in atomic number by 25, ladies and gentlemen. From barium to thallium, they differ by 25 because, again, we are not including the D's and the F's in our periodic table. Questions?
Wait, they differ by 25 because they're counting the F's.
Because we don't have the D's and the F's in this periodic table, but they do exist in the periodic table.
So in the periodic table, we count them, that's why they're different from.
So in other words, if you went from this one to this one, the atomic number would jump by 25. It wouldn't. The atomic number right here is 56. The atomic number of this element right here is 81.
Okay.
Even though they're right next to each other. Normally the atomic number would go 4, 5. Here it goes 56, 81. Here it goes 20, 31.
So you're not gonna, do we not use the atomic numbers for them? Like you're not gonna say, oh, this element.
That might be a clue. The atomic number named after the scientist who found the proton is 17.
What did I say differ in atomic?
In atomic number by 25 down here, by 11 up here. Oops, I can't write it there. What element is right here on our current periodic table, ladies and gentlemen? Pb, lead. Everything from 82 and on, even in row 7, are all radioactive elements, ladies and gentlemen. Everything from 82 and on is a radioactive element. There all the way through. All the way through.
Wait, in the 7th period, it's all the way across, or it's just those two?
Everything after 82.
Even in the noble gas and stuff?
Yes.
And the man-made or no?
Yes. Now again, we are making some generalizations here. Okay? What I mean by that is, have we really studied these man-made elements enough to know for sure every single one of them is radioactive? Probably not. But I'm not going to give you a rule and then tell you, well, except for this, and no. So our rule is everything after 82 is going to be radioactive on this periodic table. Okay? Just to keep it simple for you. Questions? Now, that doesn't mean that things under 82 are not radioactive, but it means everything 82 and after for sure are radioactive.
So the ones above are radioactive?
They could have, some of them can be, but not all of them are. But 82 and up, they're all radioactive. Go.
Can we put like the numbers on the periodic table of like the numbers that are on
You
there?
could if you want. I'm not stopping you from doing anything like that you want to. Okay? But here's the thing. I think more important than those numbers, if you have the periods numbered on the side and the groups across the top, it's fairly easy to line them up and find the spot that you're talking about. Now, if you want to take the time to write 1, 2, all the way to 118, I'm not going to stop you, but there aren't going to be that many clues where it's like, all right, the element with 14 protons is the low point of a wave. The element with 32 protons is the high point of a wave. The element with 64. No, that clue will appear maybe once on your test. Okay? So, but again, if you wish to, I'm not stopping you. Okay? Questions?
No.
Okay. What element is there, ladies and gentlemen?
One. I mean, carbon.
Carbon. Carbon is the element of life, ladies and gentlemen. All living things on this planet are carbon-based. They all are made out of carbon. By the way, not only are all living things made out of carbon, but Cynthia's writing utensil is as well.
This comes from a tree.
Really? Your plastic mechanical pencil comes from a tree.
Well, the lead does, doesn't it?
That hasn't been lead since I was in school.
It's graphite.
It's graphite, which is carbon. By the way, what other very important substance on Earth is just carbon?
Paper.
Diamonds.
It's just
Hardest substance naturally known to man. Diamonds are made of carbon.
Is that
My wife told me they were. I hope she didn't lie to me. Okay? Questions?
so then why? So why did it turn green when it's not?
Why do diamonds turn green?
No, not diamonds, but like jewelries.
It's
Like,
not
is it
Because
gold?
that's a coating covering some other metal that has a reaction with your skin. It's not real gold. Okay? So that boy who bought you that gold ring and said this is solid gold, he lied to you, Cynthia. Lied. Okay? Or that person, that special someone who bought you that. They lied to you. Okay? Making no assumptions. Questions? Okay, metals, ladies and gentlemen. Metals are ductile. That means they can be drawn into a wire. Metals are malleable. That means they can be pounded into sheets. If I were to take a hammer and hit the frame of that door, it would hold the shape that it would get from me hitting it with a hammer because it is malleable. Metals are malleable. Now, I take and hit this glass with a hammer, what happens? It breaks because it is brittle. Okay? Metals can be oxidized in redox reactions. Metals are often oxidized in redox reactions. Don't worry, we haven't explained what a redox is. They are also good reducing agents because whatever is oxidized is also called a reducing agent, ladies and gentlemen. Okay? Metals lose electrons. Now, again, ladies and gentlemen, I'm not telling you need to write any of this down, but these are all properties of a what? Metal. So maybe, just maybe, on the back side of this sheet, since there's room over here on the metal side, you write down metals and list some of these properties. Because here's what's going to happen on your test. And please listen carefully. The two elements named for the scientists who tried setting up the periodic table. Give me their names. Nope, there's only two who did it. One was German, one was Russian. Give me both of them. Meyer and Mendeleev. Okay? So the two elements named for the scientists who tried to set up the periodic table are in the same period as the number of deorientations.
SC.
The number of deorientations. How many? No.
Oh,
10.
Sync.
No.
Wasn't it 10?
No. Not the orientation. The total number of electrons is 10.
Maybe nine.
There's 5 orientations.
Okay. So what period are we in? 5. They are next to each other even though they differ in atomic number by 11.
So
38 and 40.
So they are 38 and 49. They are the second and third element in, right? The one named for the scientist whose periodic table was accepted is more malleable than the other.
how do we determine if an element is more valuable?
Well, it would be a better what? Metal. We haven't got to where the better metals are, but in a minute we will tell you that the better metals are further to the left.
So it'd be 38 or the
Mendeleev would be in 38. Meyer would be in 49. That's the kind of question you're going to get. That is an intense question, ladies and gentlemen, because you've got a lot of things to put together there, right? You got to know what number, how many d orbitals there are, 5. You got to know who the 2 scientists are. Then you got to figure out which one is more metallic. And you got to know which 2 spots are next to each other, even though they differ by 11. Luckily for you, you've been writing this down. Luckily for you, you've been writing this down. Metals are shiny, which means they have something called luster. Metals have a high boiling point. Right? Those are properties of metals. Now, you are welcome to write down all of the properties of nonmetals that we are about to give you. However, ladies and gentlemen, what do we know about nonmetals compared to metals? So if you don't want to write down all the properties, just remember that nonmetals would be the exact opposite. Yes?
Is there exceptions to the high boiling point rule?
Well, there are, but again, I'm not going to give you something like this and then worry about an exception. So in other words, we're saying that if it's going to be a better metal, it's going to have a higher boiling point. If it is more shiny, it is going to be a better metal. If it is more ductile, it will be a better metal. So that is the way we are using this. Now what that means, ladies and gentlemen, is on the periodic table, we're going to be looking for things that are either in the same group going up and down or the same period going across. And if we're looking for a better metal, the better metals are further to the left. Okay? The better metals are also further down on the periodic table, but we haven't gotten to that quite yet. We will. But that means that if you're looking for a better metal, ladies and gentlemen, you're comparing 2 spots on your empty periodic table. The one further down is the better metal, or the one further to the left is a better metal. The one further to the right would be a better, the one higher up would be a better non-metal, because again, metals and non-metals are opposites of each other. So non-metals are not ductile. They cannot be drawn into a wire.
Wait, so better metals go down and to the left, and better non-metals go up and to the right.
Beautiful.
So
Whoa, slow down. Don't put that down yet. Don't do that yet. Don't do that yet. Don't do that yet.
I can't write that down.
What?
That better metals are.
You can, metals. You can write about the non-metals, but there, as always in chemistry, there is an exception, and we'll get to that in just a moment. Okay?
Showing
Why?
it can't be drawn into a wire, and it says can.
No, ductile means can be drawn into a wire. So it is not ductile, which means ductile means can be drawn into a wire. It is not malleable. Malleable means can be pounded into sheets, just so you know. Okay? Good. Excellent. Moving on. They are reduced in a redox reaction. They are good oxidizing agents. They gain electrons. They,
are not shiny.
well, they're a lot like Mr. Nelson. They're dull. Okay? They're dull. No luster. And
They have a low boiling.
they have a low boiling point. Matter of fact, most of them are, or many of them are what state of matter? Gases.
Solid.
Gases. Ooh, ooh, ooh. This will never work, ladies and gentlemen. This will never work. Never work. All right. What element is there?
The,
Bromine.
but that one is a solid.
No.
Oh.
It's blue, right?
Wait, can you go up so I can see the number?
Can I go up? I can't.
Wait,
'Cause
yeah,
if I
never
go
mind,
up-
Never mind. Never mind.
No, I wanted to, Cynthia, but if I go up all of this stuff, then I should have started it out lower. I can't go back and change that now because all of that is written on the screen. That's underneath it. It won't move. You understand what I mean? Technology doesn't do what we always want it to. That is a liquid at room temperature, ladies and gentlemen. There is only one other element on the periodic table that is a liquid at room temperature. That is mercury, but since it's in the D block, we can't put it on there. Okay? Can't put it on there. Okay? Questions? We're good?
Wait, I didn't understand the thing that KP said, it's the metal down and the metal up.
Hang on. I'm going to show you something that'll make that more clear. Okay? By the way, another word for being non-ductile and non-malleable is to be brittle. Brittle means things break apart. They don't hold together. Questions? Good? Anyone need more time? All right then.
Wait, brittle means they break apart easy?
Yes. So for something to be ductile, for something to be drawn into a wire, for something to be pounded into sheets, there's something there that holds it together. Okay? If I hit the glass, it breaks apart. Why? Because it's not strong enough to withstand that. If I hit the metal frame, it bends. It gives. It takes a new shape, but it bends and gives. The metal does not, the glass does not. Okay? All right, so here we go. Properties of the periodic table. The most reactive metal is francium. The most reactive metal is francium, ladies and gentlemen. Where is francium? Bottom left. Bottom left. Most reactive metal. So now, Cynthia, that question that you've been asking me for the last 2 days, you can answer. Because if you're comparing two elements on the periodic table, here and here, which one's more reactive? The one on the bottom. If you're comparing two elements, here and here, which one is the more reactive metal? The one further to the left. I will not do this to you. Which one is more reactive?
The bottom one.
No, actually it wouldn't be. It would be this one. This family is far more reactive than this family is. Even though this one's at the bottom, this is still far more reactive. Okay? But again, I will not ask you to compare something like this. I will ask you to compare something like this. Or I will ask you to compare something like this. Okay? Now I can do the same thing over here, but these are what? Non-metals. Okay? So, if this is the most reactive metal, francium, what is the most reactive non-metal?
Aluminum.
Aluminum's not even a non-metal.
Oh, sorry. No.
Fluorine? Why?
On the opposite corner.
Really? I thought the opposite corner was up
OG,
here.
But that's all noble gases. We don't touch those.
Correct. That was the part that I didn't want you to get excited about. If you're talking about a reactivity trend, can you include noble gases?
No, they don't react.
They do not react. So the most reactive metal, non-metal is fluorine.
I keep going to right on there and I can't do that.
Most reactive non-metal is fluorine. So again, we cannot talk about the reactivity of noble gases. They don't have any. But we can talk about the reactivity of these two elements here. Which one is the more reactive non-metal? The top one. We can talk about these two. Which one is the more reactive non-metal? The one further to the right. So the closer you get to here, the more reactive a non-metal you become. The closer you get to here, the more reactive metal you come. Correct? By the way, the closer you get to there, the least reactive metal you become, correct? Either way, I don't care how you want to look at it.
So what's the least reactive? Is it not
The least reactive what?
metal?
I wouldn't ask you about that because it's unfair again to compare something that is higher up but further over to something that is lower. Can't do it. Okay? Because they go on an angle like this, we're not going to try to make that comparison. Because is it better to be up at the top here, even though you're further to the left,
or down further and further to the right. We're not going to make that comparison. Okay? Not going to make that comparison. Questions? Okay. So the most reactive metal is francium. The most reactive nonmetal is fluorine. Now, atomic radius, ladies and gentlemen. Now you should flip to this periodic table, because we are going to talk about atomic radius as you go across a period, and we are going to talk about atomic radius as you go down a family. Now again, when I give you this trend, understand, I don't care which family you put it in, but I'm going to give you the trend and it describes all families. I won't give you a trend that only describes some of the families. Do you understand what I mean? So otherwise, everything you would write would be in this one and up here. So if you want to spread these things out, you are welcome to. But understand, I'm talking about a trend that either goes across the periodic table or that goes up and down a family. Fair enough? So what is atomic radius? What do you think it is?
Half the distance between two covalently bonded like that.
Good. Now tell me what that means.
I don't know.
Really? What?
How big they are.
How big what are? Okay, so it's the size of an atom. That's what it is. It's the size of an atom. That is what atomic radius is. Now, yes, the definition is half the distance between two covalently bonded like atoms. The problem is it's hard because you remember the shapes that I gave you? The circle for the S in the middle, then the P's are those lobes, then the X's are those weird ones. Well, it's hard to say, okay, that an atom is truly a sphere in shape, but we do. Okay? We do. All right, so as you go across a period, ladies and gentlemen, atomic radius actually decreases. So as you go from the left-hand side of the periodic table to the right, the atomic radius actually goes down. I hope you got this, because all of it is about to go away, ladies and gentlemen. So now, the way I would do it, and I'm just going to show you one time here. That's the way I would do it. But I understand what that means. As atomic radius goes across, it goes down. If you want to write down here, smaller, I don't care. How you can understand it. Okay? How you can understand it.
So from left to right, it goes down, and from up to...
We haven't gotten there yet. Okay? So, these two elements are right next to each other on the periodic table, even though they differ by 25 in atomic number. Okay? They are the two longest wavelengths of electromagnetic radiation listed. The one with the longer wavelength is a man-made element. Okay, so let's start by finding the two longest wavelengths on this list. Microwaves and infrared. Which one is longer? Microwaves. Now we said they were next to each other even though they differ by what? Where does that mean? They're in 6 or 7. They're the second and third elements, group 2 or group 13, correct? How do you know which one goes where?
Well, you said that the longest one is a man-made, so that's the only one. The microwave can only be in one.
It has to be in unit or in period 7, spot 13. Very good catch. That was the last part of the clue. It said the one with the longer wavelength was a man-made element. That means that it can't be 6 and 7 anymore. It can only be period 7 because they are the only ones that have the man-made elements in them.
So would
So infrared, which has a shorter wavelength, would be in spot 88 where radium is. Microwave would be in the spot where nihilium is, number 113. Okay? Again, next to each other, infrared first, microwave second in the 7th period. Excellent catch. Excellent. Good job. You're starting to get this. Questions? Yes? You can do it if you want. It's your funeral. Go ahead. All right. Here we go, ladies and gentlemen. Next trend. If you are talking about atomic radius, if you are going down a family, atomic radius increases. Why? I don't care about the protons. Radius has nothing to do with protons. Protons are in the nucleus. That's the center portion of the atom. What? Not only are there more electrons, but there are more what for them to be in? Energy levels. And each energy level goes where compared to the last one? Outside of it. So what's the only thing the atom can do is you go down. Get bigger. Get bigger. So now I would flip it over, and on the other side, okay, I would definitely take, maybe this is going to work out for me, ladies and gentlemen. Maybe this is going to work out for me. As I go down, it increases. Now, that's the kind of thing I would write down. Now, again, I completely agree with what Sophia said the other day. Well, Mr. Brandon, I got my notes. Why do I got to write all this stuff down? Okay, well, you just flipped to figure out what the two forms of electromagnetic radiation are. Now you got to flip to the page in your notes where it talks about where the man-made elements are, which is not in your notes. Okay? But then you got to find out what atomic radius is doing as you go across or down. Believe me, the more you write on these periodic tables, the more it is condensed. Plus, again, you're looking at it. Okay? I'm comparing two spots and trying to figure out which one goes where here. Well, this says that atomic radius increases, so the one with the larger radius goes down. The one with the smaller radius goes up from them two spots that I'm left with. Okay? That's the kind of thing you're going to have to use. That's the kind of thing you're going to have to do.
So from left to right, atomic radius goes up. From up down, atomic radius goes up.
Wow, you lost me there because you said from up, down. So atomic radius as you go across
From left to right,
goes down.
goes down. Yeah.
Goes down. But if you go from top to bottom,
It goes up.
it goes up. By the way, why does it go down if you go across?
More electrons.
Yeah, but they're in the same energy level. If there's more electrons, wouldn't you think it would get bigger from the electrons repelling each other?
They're more attracted to the
Okay, that's the only explanation that scientists can give us. As you go across this period, ladies and gentlemen, you're adding an electron every time you move across, but you're also adding a what to the nucleus? A proton. So as that nucleus becomes more positively charged, it takes all those electrons in that same outer energy level and pulls them closer to it. It's the only explanation we can give you, because we know that is what actually happens. That's the best explanation we can give you for why. Questions? Good, 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 good. All right, ionic radius, which is different than atomic. What is an ionic radius?
ions.
The radius of a stable ion, which means what is a stable ion? Magnesium, when is it stable? But when it's what ion?
+2.
Plus 2. When is sodium stable?
When it's +1.
Plus 1. When is aluminum stable?
When it's +2.
When is chlorine stable?
Okay, so we're clear on that, correct? So when it's stable, so when it's isoelectric to a noble gas, but the main thing is when it's stable. So understand, there's different charges that they would have when they're stable, right? Okay, ionic radius. As you go across a period, it goes down, just like atomic radius. But there's an exception here. The radius of a stable ion configuration. So when you lose enough electrons or gain enough electrons that you become like a noble gas, when you are stable. Ionic radius as you go across a period decreases. But think about this. What did atomic radius do as we went across? Okay, so it doesn't surprise us that an ionic radius would do the same, correct? But here's the thing. Sodium loses 1 electron, correct? Becomes 10 electrons. Magnesium loses 2 electrons. Still has 10 electrons then when it's stable, right? So those 10 electrons get pulled closer to the nucleus. That's why it gets smaller. Aluminum, 10 electrons, correct? Loses 3. Still smaller yet. Well, what happens to silicon? You add what? 4. So here, you are losing electrons in your outer energy level, correct? How many energy levels does sodium have when it's an ion? 2. How many does magnesium have?
2.
How many does aluminum have?
2.
How many does silicon have?
2.
So what do we know about 3 energy levels compared to 2? It's bigger. That's this one-time jump. This one-time jump says that now our nonmetals are going to get larger when we jump here to here, but then what happens as we continue to go across? Nope. They get smaller again. Why? This has 18 electrons, a -4. This has 18 electrons, a -3. This has 18 electrons, a -2. This has 18 electrons, a -1. So again, they start getting pulled more toward the nucleus and they become smaller. Okay? They become smaller. You look confused a little bit, KP.
I am a little.
Okay, so what it has to do with, when these become stable, they look like argon. When these become stable, they look like, which is bigger, argon or neon? Argon. So as you go across, the radius goes down. But when you're talking about an ionic radius, because we go from losing electrons here to gaining them, there is a one-time jump where the radius becomes much higher because we're working with another energy level now.
So it goes from 2 for aluminum and 3, and then does it go back down to 2 or it stays 3?
Okay, so these would all look like neon, 2 energy levels. These all look like argon. These look like what? Argon. So again, these are going to get smaller as we go across, okay? And we're going to ignore these. They don't matter. Here, these would continue to get smaller, but then when we go to arsenic, it would go up 1 energy level, which is that one-time jump.
And then, but the rest stay that too, right?
Well, then the rest start going down again. So if you were to look at it on a graph, okay, size, it would look like this. It would start out, it would go down. Then when you hit the nonmetals, it would jump up. And then it's going to come down again. And then when you hit the nonmetals, it's going to jump up. Okay? So this jump from here to here is when you go from metal to non-metal.
Do metals have a higher ionic radius than the non-metals?
Metals actually would have a smaller ionic radius than the nonmetals. Yes. But here's the thing. These nonmetals are the first few of period 2, let's say. But this ends with the metals of period 3. Then when we get to the nonmetals of period 3, it takes a jump again.
Does that make sense?
And then in period 4, it goes back down.
Goes back down, and then when you get to the nonmetals in period 4, it jumps again. Okay? So basically, an ionic radius of a nonmetal will always be bigger than a metal in the same period. In the same period. The nonmetals will always be larger than the metals in the same period because they will have one more energy level. Questions? Now, here's the good news. That only affects you when you're going across. If you are going down, it just goes up. It just goes up. Okay? Why? Lithium would look like helium. Sodium would look like neon. Potassium would look like argon. And these things go up as we go down. Why? Because there's more energy levels. So here, lithium would have 1 energy level. This would have 2. This would have 3. This would have 4, 5, and 6 as ions, which means they still go up. They still get bigger. Questions? Some of you still, you're not saying anything, but your eyes are like, I have no idea what he's saying. Okay, I'll move on then. Electron affinity, ladies and gentlemen, is the ability to attract and hold on to an electron. The ability to attract and hold on to an electron. What element, ladies and gentlemen, what element has the best electron affinity? The ability to attract and hold on to an electron. What? Chlorine?
Carbon?
Which one has the worst? Francium. As you go across the period, electron affinity increases to attract and hold on to an electron. Okay? And then as you go down the family, electron affinity decreases. But what element is the best at attracting and holding on to its electron? Not fluorine.
Carbon?
Why? And guess what? Noble gases are what? Do you think they want to give up an electron if they're stable? No. Hydrogen has the best It doesn't say to attract and add an extra. Oh, wait. My bad. An extra electron. So you're right. Don't put the noble gas in here. I was confusing it with electronegativity. Okay? So to hold on to an extra electron, so we would not include the noble gases. Thank you. My bad. I almost missed that. I almost messed you up. So don't include the noble gases. Fluorine is the highest. Francium is the lowest. Why? Metals want to do what with electrons? Get rid of them. They're willing to. Hey, you want one of mine? Take it. Go away. Non-metals are like, I need an extra one. You ain't getting it from me. Questions?
So from left to right, electron affinity increases,
Goes up.
and then from top to bottom, it decreases.
Perfect. You got it. Questions? Electronegativity is the tendency of atoms to attract electrons to itself when combined with another atom. So guess what's not included in this? Good. Noble gases. Why? They don't combine with another atom. Right? Okay? So what atom has the best electronegativity? Fluorine. Which one has the worst? Francium. So you go across, electronegativity increases. As you go down a family, electronegativity decreases. What? You don't have to. I don't care. But when the question says these two elements that are in the same period, and this one has a higher electronegativity than the other, you got to know which one's to the left and which one's to the right. Or these two elements are in the same family, and this one has a higher electronegativity. You got to know which one is which. Questions? It's a lot of stuff. It is. That's why I let you use your notes. That's why I'm letting you use your periodic tables. That's why I'm letting you use your computers on the test. Because it's a lot of stuff. Ionization energy, ladies and gentlemen. Ionization energy. The energy needed to remove an electron from an atom or ion in its ground state in the gaseous phase. In other words, the amount of energy needed to get an electron away from an atom. If you need more energy, guess what? That means it's harder. If you need less energy, that means it's... What element has the lowest ionization energy? What? Francium. Why? And it wants to do what? Get rid of an electron. So guess what? To convince francium to get rid of an electron, woohoo! Not a problem. Here, take it. What one has the highest ionization energy? Helium. Why? Because it's stable. Doesn't want to lose an electron. Doesn't want to lose an electron. So as you go across a period, ionization energy goes up. What happens as you go down a family? It decreases.
So wait, the other ones like the electron affinity and the electronegativity.
Do not include the noble gases. This one does. This one does. Last one, ladies and gentlemen. Electron shielding. That is the reduction of attractive forces between the nucleus and the outer electrons by the inner electrons. In other words, positives and negatives do what to each other? Attract. But if you put a negative by a negative, what does it do? Repel. So while electrons want to be attracted to the nucleus, if there's other electrons in the way, they create what is called electron shielding. Okay? So as you go across a period, electron shielding is constant. Why? Because there's the same amount of electrons between the outer ones and the inner ones, no matter where, when you go across. Okay? But as you go down a family, what happens to the shielding? Why? Where does that next energy level go compared to the other one? On the outside. So guess what? In the second energy level, there's only one set of electron shielding. In the third energy level, there are two. In the fourth, there are three. In the fifth, there are four. So electron shielding increases. Questions, ladies and gentlemen? If you're missing labs, you got 2 days to turn them in. Till Thursday, you got to turn them in. Some of you, it may be the difference between passing and failing this class. And if you're failing right now, and you're going into the final exam hoping that you'll do well and make your grade passing, that is a possibility. But I would try to get to passing before you go into the final exam with a retake if you need it from the last test. I'm telling you this, if you don't pass any of my tests, there's no way you're passing this course. And if you haven't passed Unit 5, Unit 6, or Unit 7, the chances of you passing Unit 8 test are not great, ladies and gentlemen. Only because you have established that you are not understanding things as we go along. Doesn't mean it can't happen, but again, do the best you can to set yourself up for success, ladies and gentlemen. You can, sure. But I'm telling you, more than likely tomorrow during home base, we're going to have a fire drill.
What?
Tomorrow or Thursday. We got to get one in this week, and they're going to do it before the end of the week. You can come in. The worst that'll happen is we have to leave. But again, I'm here in the morning too.
I'll get here in the morning.
So
Me too. I'll be here. Will you? Yes. Maybe.
have a great day, ladies and gentlemen. Goodbye, goodbye, goodbye. Go away. See ya. Goodbye. Adios. Arrivederci. Goodbye. Today after school? Okay, then not. That's fine.
Correction. I need
Well, then
one
you can't
more.
come in today after school.
I need one more.
Well,
What
then
if I
maybe you should
finish
come in
it?
and see me and do the corrections after school.
Okay.
But again, you got today, tomorrow, Thursday.
Can I retake the last one that I didn't even do?
The last one. Hold on a minute.
Yeah, where we have